Welcome back to G Fun Facts Online. Today we're going to challenge a fundamental fear of the ocean, and we're going to do it by looking at a piece of metal that refuses to sink. For as long as humanity has ventured onto the water, we have been haunted by the specter of the unsinkable ship. It is a term laden with hubris, most famously associated with the RMS Titanic. That vessel was a marvel of 1912 engineering, featuring 16 watertight compartments. The theory was sound. If you have enough reserve buoyancy and enough sealed chambers, you should float. But as history tragically proved, that is a statistical game. If the tearing force of an iceberg is strong enough, the geometry fails. For over a century, this has been the rule. Things float because of their shape and their displacement. But what if the material itself refused to sink? What if buoyancy wasn't just a function of hull geometry, but an intrinsic property of the metal itself? That is the question we are exploring today. We are looking at a breakthrough from a laboratory at the University of Rochester, where a team led by Professor Chunlei Guo has turned science fiction into reality. By blasting aluminum with femtosecond laser pulses, they have created a metal that defies the standard laws of wetting. It does not just float. It actively fights to stay on the surface. Even when punctured, slashed, or held underwater for months, this superhydrophobic aluminum carries its own life jacket of air, a silvery sheath that renders it effectively weightless in water. As of January 2026, the team has unveiled their latest iteration, a scalable tube design that promises to revolutionize everything from oceanographic sensors to the very hulls of future ships. To understand how this is possible, we have to leave the physics lab for a moment and look at biology. Nature actually solved the problem of unsinkability millions of years ago, specifically in the muddy ponds of Europe and the flooded rainforests of Brazil. We need to talk about the diving bell spider and the fire ant. The diving bell spider, or Argyroneta aquatica, is an evolutionary anomaly. It is a spider that lives its entire life underwater, yet it does not have gills. Instead, it survives by engineering a physical gill. The spider weaves a dome-shaped web between underwater plants and fills it with air brought down from the surface. But the key to its survival lies in its own body. The spider's abdomen and legs are covered in fine hydrophobic hairs. When it surfaces, these hairs trap a thin layer of air, giving the spider a silvery appearance underwater. This trapped air layer is known as a plastron. It serves two functions. First, it acts as a scuba tank, allowing gas exchange with the surrounding water. Second, and most importantly for us, it provides buoyancy. The spider is, in effect, wearing a suit of air that water cannot penetrate. Now consider the fire ant, specifically Solenopsis invicta found in the floodplains of Brazil. When the waters rise, the colony does not drown, they assemble. Thousands of ants link their bodies together, gripping each other's legs with mandibles and tarsal claws to form a living raft. Individually, a fire ant is slightly denser than water and would struggle to float, but collectively, their water-repellent exoskeletons trap millions of tiny air bubbles between their bodies. This trapped air reduces the overall density of the raft to far less than that of water. You can actually push a fire ant raft underwater with a stick, and it will deform, bending like a rubber mat, but it will not sink. The moment you release the pressure, it springs back to the surface, its air pockets intact. Professor Guo and his team looked at these two biological marvels and asked a simple question: can we do this with metal? To make aluminum act like a spider's leg, one must master the physics of wetting. This is the interaction between a liquid and a solid surface, governed by something called the contact angle. Imagine a drop of water sitting on a table. If the surface is hydrophilic or water-loving, the drop spreads out flat. The contact angle is low, less than 90 degrees. The water wets the surface, pushing air away. This is what happens with standard aluminum. If the surface is hydrophobic, or water-fearing, like a waxed car or a Teflon pan, the water beads up. The contact angle increases to above 90 degrees. But to achieve what the spider does, we need to go further. We need to reach the superhydrophobic state. This is the holy grail of surface science. In this state, the contact angle exceeds 150 degrees. The water droplet becomes a near-perfect sphere. It barely touches the surface, sitting on top of the texture like a fakir on a bed of nails. This specific condition is known in physics as the Casey-Baxter state. In this state, the water droplet doesn't actually touch the bottom of the grooves in the material. It sits on a composite surface made of the solid metal peaks and the air pockets trapped in between them. There is a mathematical formula for this, involving the fraction of the solid surface in contact with the liquid. The goal is to make that solid fraction tiny. If you can etch billions of nanoscale pillars into the metal, the water is mostly touching air. And since water holds together tightly due to surface tension, it refuses to break that tension to fill the gaps. It beads up and rolls off. The problem with standard superhydrophobic coatings, like those spray-on repellents you might see in infomercials, is durability. They are chemical layers. They can be scratched off or degrade over time. Professor Guo's team realized they needed a structure, not a coating. They needed to carve the hydrophobicity into the atoms of the metal itself. To do this, they used a femtosecond laser. To appreciate the precision of this tool, consider the time scale. A femtosecond is to a second what a second is to about 31.7 million years. This technology relies on chirped pulse amplification, or CPA, a technique that won Donna Strickland and Gerard Mourou the Nobel Prize in Physics in 2018. Standard lasers melt metal. If you fire a continuous beam or even a nanosecond pulse at aluminum, the metal heats up, melts and reforms as a messy blob. It destroys the delicate microstructures you are trying to create. Femtosecond lasers are different. They deliver energy so fast that the atoms are ionized and blasted away before they have time to transfer heat to their neighbors. This is called cold ablation. It allows for the creation of incredibly intricate features without melting the surrounding material. In the University of Rochester lab, the laser scans across a 1-inch aluminum disc to create a hierarchical structure. First, on the microscale, it carves deep parallel grooves or pits, measuring roughly the width of a human hair. Then, on the nanoscale, right on top of the ridges of those microgrooves, the laser etches tiny bumps and chaotic, coral reef-like structures just nanometers across. This dual-scale roughness is critical. The microgrooves provide durability and space for large volumes of air, while the nanostructures amplify the water repellency to extreme levels. The result is a surface that is pitch black, because the structures trap light as well as air, and so water repellent that droplets bounce off it like rubber balls. But creating a superhydrophobic surface was only step 1. Step 2 was making it buoyant. Simply etching a block of aluminum won't make it float, because aluminum is denser than water. To achieve buoyancy, the researchers had to trap enough air to counteract the metal's weight. The breakthrough came with a specific geometric configuration. In 2019, they developed a sandwich design. 2 laser-etched aluminum plates were placed facing inward, separated by a small gap. The superhydrophobic surfaces faced each other. When submerged, the water could not enter the gap between the plates because the hairy metal surfaces repelled it. This created a waterproof compartment containing nothing but air. Unlike a sealed hollow sphere, this compartment was open to the water at the edges, but the surface tension was so strong that the water simply refused to enter. By January 2026, the team refined this into a tubular structure, publishing their results in Advanced Functional Materials. In this design, the inside of the tube is etched. When the tube is tossed into water, air is trapped inside the core. Because the etching is on the inside, it is protected from abrasion and external damage. They tested these structures ruthlessly. First, they performed a puncture test. In a normal hollow vessel like the Titanic, a hole releases the air and lets in water. But in the laser-etched tube, they drilled holes and found that the water still refused to enter. The edges and interior surface remained superhydrophobic, keeping the air bubble trapped and the tube afloat. Then came the submersion test. They forced the metal underwater and held it there for 2 months. In standard superhydrophobic materials, the air usually dissolves into the water over time, a failure mode known as the Wenzel transition. But Guo structures retained their air plastron, bouncing back to the surface the moment the weight was removed. The implications of this eternal buoyancy extend far beyond cool physics demonstrations. Let's talk about the future economy of this material. The first obvious application is the unsinkable ship. While building an entire hull out of femtosecond etched aluminum is currently cost-prohibitive, the technology could be used for critical buoyancy modules. Imagine lifeboats or emergency flotation devices made from this material. If a ship's hull is breached, these etched internal structures would refuse to flood, providing reserve buoyancy that never fails. Then there are oceanographic sentinels. We are currently littering the ocean with sensors to monitor climate change, salinity, and currents. These devices need to float for years. Current buoys rely on foams, which degrade, or hollow shells, which can leak. A laser-etched metal buoy would be practically immortal, immune to the crushing pressure that collapses hollow spheres and the degradation that destroys plastics. There is also the potential for energy harvesting. The January 2026 update from the lab highlighted that the buoyancy of these tubes is recoverable and highly responsive. A raft of these tubes could ride the waves, bobbing with high efficiency to drive kinetic energy harvesters, without the risk of waterlogging over time. Furthermore, there is the concept of the plastron economy. Beyond buoyancy, that stable air layer reduces drag. A ship hull that holds a permanent layer of air would slip through the water with significantly less friction. This is the lubricated transport dream of naval engineering, potentially cutting fuel consumption by 10 to 20%. However, we must address the challenges. If this material is so perfect, why aren't we building the Titanic II out of it today? The first hurdle is the cost of time. Femtosecond laser etching is a serial process. It is like drawing a picture with a single fine point pen. To cover a square meter of aluminum takes a significant amount of time and energy. As of 2025, industrial femtosecond lasers have reached kilowatt levels, allowing for faster scanning, but coating the thousands of square meters of a ship's hull remains an economic bottleneck. The cost is currently estimated at thousands of dollars per square meter for the processing alone. The second challenge is the biofouling battle. While the metal repels water, the ocean is full of things that aren't water. Proteins, bacteria, and barnacles are persistent. Over months and years, a biofilm can form on submerged surfaces, masking the superhydrophobic texture. The inward-facing design helps this by shielding the active surface from direct contact with open ocean biology, but long-term deployment remains a hurdle that requires field testing. Finally, there is the durability of the nanostructure itself. Aluminum is a soft metal. While the tube design protects the etched surface, severe crushing or abrasion could smooth out the nanofeatures, destroying the effect. Researchers are investigating etching harder materials, like titanium and steel, which are tougher but more difficult to process. In conclusion, the work of Chunlei Guo and his team at the University of Rochester represents a fundamental shift in how we think about materials. We are moving from the chemical age, where we coat things to change their properties, to the structural age, where we reshape matter itself to do our bidding. This laser-etched aluminum serves as a reminder that the properties of a material are not just defined by what it is, but how it is arranged. By borrowing the geometry of a spider's leg and the cooperative physics of fire ants, we have created a metal that refuses to sink. It is a triumph of biomimicry and laser physics, promising a future where our ships are safer, our sensors are more durable, and our relationship with the ocean is a little less precarious. For now, the unsinkable metal sits in a tank in a Rochester lab, a small silver ring floating defiantly on the surface, holding the promise of a fleet that will never know the bottom of the sea. Thanks for listening to G Fun Facts Online, and we will see you in the next episode.